I'm going to be talking about hardware acceleration of a specific VDF construction, and that is the RSA VDF construction. And what I'll talk about today is I want to just give a sort of a background on sort of how this work was completed and what the results of the work is, but also I want to provide a number of links for folks if they want further information to go in and read more about this work and ideally to join in and participate in the work that's going on around this hardware acceleration topic. So just to begin and give folks a little bit of background, while I'm presenting this talk, ultimately this work is the culmination of a large number of participants in the VDF Alliance. And folks may not be familiar with the VDF Alliance, but it's a collection of academic, nonprofit, and corporate collaborators that are building open source software to improve the security, scalability, and privacy of blockchain protocols. And really the goal of the Alliance is to use hardware acceleration to make these emerging cryptography techniques more practical. And I'd really urge anyone that is really interested in this topic and would like to learn more to visit both vdfresearch.org, which is a fantastic resource maintained by Justin Drake, who will be presenting next, and also vdfalliance.org. And just to give some folks some context for some of the activities that happen within the VDF Alliance, we generally have weekly calls where we talk about the progress and the state of the art in VDFs. This undertaking to actually bring VDFs into production is sort of a multifaceted research project that involves, expertise in cryptography, in theoretical lower bounds research, in multi-party computation. And so if you have interest in any of these areas and actually looking at how we could bring VDFs into production, really urge folks to take a look at the various websites that I mentioned, and please, reach out and let us know if you'd like to contribute in this. We do generally have a VDF day once or twice a year. We most recently held one at Stanford during the Stanford Blockchain Conference. And if this is something you're interested in attending in the future, there is a sign up on the vdfalliance.org website where you can get more information and be notified about these things. So just to provide, a last bit of context, Joe did a great job talking about sort of the three main functions of a VDF. In terms of hardware acceleration, the two things that we're really going to be looking at is both the eval function, which in the case of RSA VDFs is iterated modular squaring, and the proof function, which is where you generate a cryptographic proof that can be efficiently verified. And this activity is ultimately about making modular multiplication as quick as possible. So, one question to ask is why hardware acceleration? So as Joe had mentioned previously, there are limitations and sort of theoretical results about how much the overall VDF can be sped up. But as he alluded to, there are ways to speed up the individual iterations, and that's really what this talk is going to be focused on. And what I'd like to sort of give some context for is why this is actually an important activity. So just to start, at a very high level, really the goal of these VDFs is to take some sort of pseudo randomness, whether that be stock prices, whether it be blockchain data or sports scores, and create this strong randomness that is unpredictable. And in order to do this, what we have to do is we have to make sure that even someone with an extremely fast, maybe they have maybe they're running at 10 gigahertz or 20 gigahertz or something like that, ensure that they can't reach that output before they have to choose and make a contribution to this pseudo randomness. And so the very simplistic way that I like to think about it is essentially in the VDF protocol, people have to choose a direction that they want to drive a car. They're going to do some number of iterations by driving to that car. And then when they get to a certain distance, they're going to find an output. And that output is ultimately the strong randomness. And so the main goal is to make sure that even if someone is very, very fast with, has very fast hardware, that they can't drive that full distance and get the output before they have to contribute this pseudo randomness. So in a very simple example that we have right here, we have your average user, and maybe he's running on a normal laptop or a desktop, and we can think about him as computing this VDF at something like 10 miles per hour. We may also have an attacker who wants to be able to bias this randomness, and he may be much faster. And this ratio between the average user and the attacker is something that we call Amax. And ultimately, the goal of all of this hardware acceleration research is to minimize this Amax number. So in this very simplistic case, if an attacker has, say, 2 hours to contribute to the pseudo randomness, and he's moving at 50 miles an hour, we need to make sure that he has to travel at least 100 miles so that he can't know what the output is at the end of the road, sort of when he picks his direction that he wants to travel. And in this case, that delta, or that A max, is 50 divided by 10 or 5. So why do we want to minimize this A max? Well, when you take these VDFs and you move them into production, A max dictates a variety of parameters for your randomness, such as how many concurrent VDFs you need to run or how often you get randomness output. So for instance, if the attacker is 5 times faster, your average user is going to have to run 5 VDFs concurrently to get the same number of outputs as the attacker, or they're only going to be able to produce an output once every 5 of these contribution periods. So all of this effort that's gone around reducing, sort of the time to evaluate this for the average user helps in a variety of ways. One, we get faster time to randomness. So we don't have to run the VDFs as long before we get randomness output on the chain. The second is that we can get more frequent randomness for the same number of chips. The third is that we have to run less of these VDFs in parallel, which reduces the overall sort of operational costs of running these systems. And then last but not least, one of the main benefits of VDFs as a sort of proof of work is that they require a lot less energy consumption. And if we can reduce the number of these VDFs that have to be run in parallel, then we reduce that energy consumption even further. So the first thing I'll talk about is the VDF evaluation. As Joe mentioned, really we sort of know from a theoretical standpoint that this modular squaring operation can't be sped up any more than just doing the iterated operation itself. But as you mentioned, there are actually ways to speed up a single iteration. And the two things that we look at here is, the first one is algorithms. And these are not algorithms that speed up the VDF, but these are hardware and multiplication type algorithms that enable you to do these squarings faster than other algorithms. And then the second one is how fast does the VDF run? So every hardware has a set of resources to do these modular squaring operations. And by using custom hardware like FPGAs and ASICs, you are able to do a single iteration of the VDF faster. So to provide just some context for sort of how quickly this hardware acceleration has been progressing, Joe and his team at the Applied Cryptography Group at Stanford, I believe they first introduced the concept of VDFs in around June of 2018. By around March of 2019, the VDF Alliance had both developed a novel algorithm for doing fast modular squaring and also implemented this on an FPGA. Again, as Joe also mentioned, this was used to solve a 20-year cryptographic puzzle that ended up, while it wasn't the first person to solve the puzzle, it was on the order of about 20 times faster than the person that solved the puzzle first. And then since then, since solving that puzzle, we went and did a $100,000 open source hardware competition where we ultimately got another 2x performance improvement for the VDF. And we've now completed an ASIC design of the VDF as well. So, without going deeply into the details of exactly how this is possible, the sort of net takeaway on the evaluator is that we've been able to increase the speed of computing a single 24-bit modular square from about 1,000 nanoseconds per squaring on a CPU to around about 5 nanoseconds on an ASIC. And what this means in practice is that we've actually, if the average user has one of these ASICs, or the average participant in the VDF protocol has one of these ASICs, we basically have to run 200 times less of these ASICs in parallel. We can get 200 times as much randomness delivered on chain, and the energy consumption is ideally also about 200 times less. So, it's been a really interesting thing to look at something like VDFs that were thought to be not able to be, sped up greatly, and actually realized that, through the use of custom algorithms and custom silicon, we're able to actually speed them up by about, over a couple orders of magnitude. To give you an idea and some context for exactly why this happens is when you do a VDF on a traditional CPU, like an iPhone or an Intel laptop or something, there's a set amount of hardware that you're in, a fixed sort of hardware configuration that you're working with. So most architectures today are 64-bit architectures, and they have 64-bit multipliers. And what this means is that if you want to do a 2048-bit squaring, then you actually have to do, you have to use these multiplication units, dozens of times. And what we're able to do through both FPGA and ASIC type architectures is that we're able to actually do these 2048-bit squaring all in a single operation. So we can actually make the multiplier, 2, 4, maybe even 10 times bigger than what's actually possible on a CPU. So I'm not going to go, very deep into the details here, but we do have an open source implementation of a VDF evaluator today. It's a fully parameterized design, so this design can be used to support other cryptographic curves and curves of different sizes. Today, the way that the curve or the implementation is done is that it uses a collection of 512-bit multipliers that sort of all operate in parallel, and then we have sort of a large reduction tree that then gets you to your final modular reduction. But what I would advise is that if folks do want to learn really more about these specifics here, we have a whole design series on medium.com/supernational that will walk through this design. And if you're interested in learning more about how hardware can accelerate not just these VDF functions, but sort of other cryptographic functions, I would invite you to watch the hardware acceleration talk delivered by Simon Peffers at day 2 of the 2020 Stanford Blockchain Conference. So, kind of the net of the state of the art for VDF evaluation is that we have an implementation today that runs on an FPGA, and it's about 20 times faster than what happens on a CPU. It runs in about 70 nanoseconds per iterated square. And we have line of sight to implementing this on custom silicon and bringing that down roughly, another 10-fold. So the next thing that I'm just going to talk about briefly is sort of the state of the art in VDF proving. So again, evaluation is just one part of this AMAX calculation. And what we want to do is generate fast VDF proofs as well. And the results that I'll show use an algorithm that was originally developed by Benjamin Wesolowski, who was, I guess, the first person to actually create an instantiation of a verifiable delay function. This algorithm was then enhanced by Argonne Design and was further improved by the VDF Alliance. The key thing here about the VDF proving is that it's very amenable to parallelization. And so what we've been able to do is basically remove almost all of the sequential operations out of generating the VDF proof so that you can sort of spread out this computation as much as possible. And we can look at a variety of designs like FPGA, GPUs, and ASICs for this. So just to give you, a quick idea of what that looks like, this is a look at modular multiplication in terms of millions of operations per second on a variety of platforms. And what we see is that we're able to get about a 35x improvement in proof generation time by using a GPU platform. And the reason that this is that GPUs really just have thousands of tiny cores that we can leverage to do this highly parallel work. And one of the interesting things that we find about this work is that these primitives that we're accelerating, modular squaring, modular multiplication, modular exponentiation, they underline a wide variety of cryptographic primitives. And so what we're hoping to do sort of as we move forward is to use these fast GPU implementations to improve things like faster snarks, to provide better strong randomness, to maybe provide anti-spam protection in certain protocols. And so that's sort of one of the things that we're quite excited about is taking these learnings that we have from this hardware acceleration and then applying it to other cryptographic primitives. Great. So I know that's been a sort of whirlwind tour of the state of the art, but just to talk about some of our future plans, I think the first thing to say is that VDF hardware is available today, and it's already been used, right? So we were able to crack a 20-year-old time lock puzzle that was supposed to take 35 years, and we did in about a month. We also have an RSA VDF service that's running using block hashes from the Ethereum blockchain. And so sort of as we move forward, we have two main goals. The first is to support projects with this VDF as a service. So if you're a project that it needs strong randomness and, say is operating on the Ethereum blockchain or another blockchain, one of the things that we can do within the VDF Alliance is actually provide you with this fast VDF hardware. The way that this VDF service works is that it's basically an API-based portal where a user can submit some randomness in. We'll evaluate the VDF on that FPGA instance running in the Amazon cloud. We'll generate a proof using an Amazon GPU instance, and ultimately this will get returned to the user and can be efficiently verified on chain. So that's the first thing that we're looking forward to do. And then the second is that we're looking to move forward and actually prototype an ASIC. So we're hoping that by the end of this year, the ASIC design is sort of fully ready for tape-in, that we could tape in the design in the first half of next year, and that by maybe the second half of next year, we will actually have operating RSA VDF chips that can be used in production systems. So that's kind of the conclusion of the state of the art on hardware acceleration of these RSA VDFs. All of the work that we've done is open source. If you'd like to see the code for this, you can go to github.com/supranational/hardware. And there's a variety of resources on vdfresearch.org and also the Medium blog series if you'd like to learn more about some of the work that was done here.